Okay, good morning, everyone. I hope you had an excellent conference. That's the last day, so one last push before the last lunch, and I hope you'll enjoy this presentation. We are going to talk about how and why you can and should run high-performance AI workloads in virtual machines. So I'm Ezra Silvera. I'm a senior technical staff member at IBM, and with me is Michael.
Good morning. Thank you for coming. I'm Michael Hrivnak, a distinguished engineer at Red Hat. Been involved one way or another with KubeVirt and related things, and especially putting Kubernetes on-prem and at the edge for quite a number of years. And very happy to see you. I'm going to turn this over to Ezra and hang out down here until a few minutes from now.
Okay, so what is the plan for today? I will go through a very quick background and motivation for the work, then present a couple of few key technical challenges we encounter and how we solve them, and also how we think this should be solved looking ahead. Then Michael will take us through real concrete customer use cases where they actually use this technology and this direction. And we will wrap up with a short summary. So quick motivation, and again, Michael will walk us through some real customers' use cases, so you will see the motivation there as well. But in general, we know that when you use virtual machines, you can improve flexibility. We can spin up a very complex environment very quickly. It allows you also horizontal and vertical scaling quite easily. We can add GPUs to VMs. We can add VMs to clusters. By the way, throughout all this presentation, when I'm talking about VMs, we are talking about few use cases where one of them is that the VM is the compute node of the Kubernetes cluster, right? So this is why we are talking about horizontal scaling and so on. We can enlarge the cluster. One key item, and which is very important to customers, is the isolation. We know that VM give better isolation, and this is especially important because it allows you to, for example, partition the specific node, single node, to multiple tenants, right? So this is very important. And the last point, and Michael was wearing the KubeVirt shirt, if you are managing your VMs through Kubernetes, then you get uniform, single management platform to manage your containers and VMs. So we keep talking about VMs. Unless I'm mistaken, we are at KubeCon, right? So the missing link is the KubeVirt project. So let me give you a very brief background on KubeVirt. So KubeVirt allows you to run virtual machines natively in Kubernetes. It does that by extending Kubernetes through an operator and CIDs. And this basically allows the user to use all the tools that you already know from Kubernetes, kubectl, kube API, CIDs, whatever. You can use those to manage your VMs. Under the hood, it uses standard QEMU, KVM, libvirt, to spin off and manage the VMs. And the VMs, if you're familiar with VMs, with virtualization, so the VMs can be represented. You can manage them and look into them through a regular VM XML. This is the XML that represents the resources and so on. I'm mentioning this because we will touch that later on. A brief history about KubeVirt. It was first released in 2017. It's an incubating CF project since 2022. However, it is a very stable and production-ready solution. A lot of customers are already using it in production. For example, NVIDIA GeForce Now, even in the financial sector, Goldman Sachs and so on, so it is used a lot. So let's jump in directly into some technical issue and not leaving you in a high-level issues. So I want to talk a little bit about performance. Now, When we are talking about virtual machines and say performance, immediately people say, oh, the virtualization overhead. So no, we are not going to talk about that because usually in AI workloads, we are doing pass-through of the devices, the GPUs, the NICs, and so on. So there are already solutions out there, or commercial and so on, that you can see that the difference between running pods on bare metal and running VMs in terms of the virtualization overhead is minimal. It's almost identical performance. The problem here is that we are doing it through the Kubernetes layer, through KubeVirt. So we are bound to whatever KubeVirt is doing. If you are creating the VM manually, I mentioned the XML before, you can tweak whatever you want. But here we are bound to that. And we encounter cases in which the generated VM was not optimal. Now, not optimal, it can be in many senses. In our case, we found out that, for example, the PCI topology that we saw in the VM was not the actual PCI topology we had in the underlying hardware. The concrete example, we had a 2-node NUMA machine, and in the VM, all the devices were attached to a single PCI root. You can expect this is obvious that the CPU to GPU and vice versa performance will be impacted by that. I just need to mention that the GPU to GPU performance probably will not be affected because this is being done over the NVLink and NVSwitch, which are not related at all to the PCI topology. So what's that? Oh, you got an update fail on something. Okay, so luckily, KubeVirt has a very nice mechanism that allows you to inject XML changes, VM XML changes, or even the whole VM XML, just before it launches the VM. So there is, if you remember, I didn't put a lot of details on that, but in KubeVirt, we have a Virt launcher pod that spin up the VM. And we can put a sidecar in that pod and inject, we get this sidecar is being called just before the VM is launched. We get the VM XML that KubeVirt wants to use. We can tweak it and inject it back. So here you can see an example. I hope you can see it. So on the left side, you can see the XML we actually changed. We used PXB extension bus to reflect the fact that we have 2 NUMA nodes. And you can see on the right side, it's very clear, the difference, and very expected. You can actually count and see that there were actually 4 GPUs. This is an 8 GPU board, H100, with 4 NV switches. You can see that there are 4 GPUs that were misaligned, and therefore we suffer from the performance. After the fix, this is the orange one, you see that everything is in the same level and it's working nicely. Now, when this is a major issue like the topology, the nice and smart KubeVirt people, some of them are here, I see, are going to work on that, and eventually KubeVirt will not have that problem. But I want to emphasize that you as a user has the ability to inject stuff, and this is a dynamic solution. It's not a change that we did a priori. While the sidecar is being called, we dynamically look on the underlying infrastructure. What is the PCI topology? We look on the generated XML, see the differences, and analyze it, and decide whether to fix or not. So it's a very powerful tool to other things as well. So this is one issue. The main challenge we encountered was actually how to integrate the VM management tools that we are using, Kubernetes and KubeVirt, with the NVIDIA tools. And here I want to give you a very brief background to people who are not familiar with NVIDIA Fabric Manager and GPU partitions. So in general, there are 2 options. We're talking about the case when I want to create multiple VMs on the same node. So suppose I have 8 GPUs and 4 NV switches. Those are the NVLink switches from NVIDIA. I now want to create 2 4 GPU VMs. So I have 2 options. One is the naive one. Let's create a VM, pass through 4 GPUs, and half of the NV switches, right? Let's take 2 NV switches. So this will work. However, you will not get the maximum bandwidth between the GPUs because you are not using the whole all-to-all networking of the NV switches, only part of the links. So the recommended way NVIDIA suggests is to take the NV switches and assign them to a different management entity. It can be a pod or VM. They call it service VM, service pod. And in that pod or that VM, we use the Fabric Manager. It's a utility from NVIDIA that will be in charge of configuring the NVLink and NV switches so you will get maximum bandwidth. It does that by enabling or activating and deactivating GPU partitions. So here I need to be careful because everyone that hear about GPU partition, you immediately think about dividing the GPU itself, right? vGPU, MIG. So no, here GPU partition, what we mean is there is a predefined set of groups of GPU that NVIDIA defined, and those are the only combinations they support for VMs. So you have illustration here. For example, on the 8 GPU board, we can have single GPU partition, 2 GPU partition, 4, and 8. You cannot create 3 GPU VM using this method. In addition to that, and this is the most important thing, those are predefined partition. So even this GPU, what are the GPUs that are used are predefined, meaning that if you now want to create a VM with 2 GPUs, it's not like you can use any combination of 2 GPUs out of the 8. No, you have only those 4. So you can also see that there will be dependency, right, or overlapping. If, for example, I'm creating a VM with this partition, so immediately I use that GPU, so immediately I can no longer use those partitions. And someone needs to know about it, right, and not allocate them. So there is a complex management thing here. Now, again, if I would do everything manually, then there is no real orchestration or integration problem. The flow will be quite simple. I'm going to the Fabric Manager, ask to activate a partition, see what are the GPUs, create an XML for the VM that includes those exact GPUs, calling libvirt or whatever, and create the VM. However, we are using Kubernetes. And unfortunately, if we are using device plugin, I will talk about DRA, we cannot control which GPUs are going to go to the pod and therefore to the VM. So you can see what happened. We can activate a partition from NVIDIA. This will be the green one. And then when we create a pod, it will select the red one. And we have no control over that. And this is a kind of mismatch and a problematic issue. So the way we kind of solve it, and this is a working solution, I said POC because we believe there is a better way to do that. So what we have done, we actually implemented our own device plugin. Device plugin, just a recap, this is the driver that is in charge of interacting with the actual resource and managing it. So what we have done, we took advantage of and there is an ongoing API between the kubelet and the device plugin. So what we have done is quite simple. At least on the slide, it's simple. So we took advantage of the get preferred allocation call. This is a call where the device plugin can say, oh, look, on the next allocation, those are the devices I prefer you will use. So what we are doing, as soon as we get that call, that kubelet wants to allocate 4 GPUs and what are the preferred devices, we go immediately to the Fabric Manager, we activate the partition, get the exact information on the GPU, return it back to kubelet, and then hopefully, I'm saying hopefully because at least on the spec, it's an optional call that Kubelet may ignore. Hopefully, Kubelet is using those devices when it reaches the allocation call. On our case, it always was the case. However, we also add some double check inside to verify that it indeed using the correct GPUs. A quick look on what we have done, on what we got. So here is the case. We created everything automatically integrated. We create 2 VMs with 4 GPUs on the same node. You can see, and here is what I said, that this is the maximum bandwidth. You can see on the top 2 panels. I hope you can see it in the details. Okay. I barely see it on the screen. You can see that there is an NV18, which means we get all the 18 links of the GPU, and I mentioned that before, and we run the nickel GPU to GPU bandwidth test. You can see we get, and this is done simultaneously on both nodes. You get maximum bandwidth between the GPUs. This is almost identical to the bandwidth you are getting on pods on the same test. So this is working. Now, I must admit, and this is why I called it POC, although we even develop it for a customer, there are a few issues with this approach. First, all the errors that will happen, for example, if Kubelet decide to choose other devices and I fail the call and everything is done below the scheduling layer, right? Below the scheduler, below the placement and selection. The scheduler is not aware of those crazy partition, the dependency and all of that, which means that it may retry the exact same thing over and over again. And I must admit, this is the worst user experience, right? Because it's nice that something is failing and then you try something else, right? You have nothing to do here. So this is one issue, and one quite technical issue is that there is no delete call in the device plugin API. And our solution for cleanup was very complex. Due to that, it was very hard to synchronize between these things, especially that we need, in order to deactivate the partition, some internal information about the GPUs that we don't have. So I will conclude the technical part with some optimistic view for the future, right? So as usual in Kubernetes, we have DRA to help, right? This is the holy grail of everything. So here, actually, DRA is a perfect match to address our issues. I will not go through what is DRA. On the context of this call, on this presentation, you can think of that like PV and PVC, right? We have the resource and we have the claims. When you want to use the resource, you are using the claims against the resource. So here, you can imagine that the possible solution is relatively straightforward, right? We can create claims that match the legitimate GPU partitions from NVIDIA. And then whenever if the user is indeed using the claims we defined, he always will end up with legitimate partition. In addition to that, you get built in the managing of the overlapping of the dependency between the partition, right? Because if we are using some unique identifier for the GPU in the selection of the resource claim, so for example, the PCI address or GPU ID, then obviously if you used a claim with a specific GPU, you would no longer be able to use any other claim that includes the exact same GPU. So this is a work in progress in KubeVirt. It should contain some code in KubeVirt itself, in addition to implementing the device, the DRA plugin itself. So with that, I've finished with this technical stuff on what we have done, and I will let Michael come and speak about what customers and what people are actually doing with that. Michael, please.
Thank you, Ezra. So all of these are tales based on a true story. Starting from the simple to the more complex, and some of this is going to be totally unsurprising. Oh, we've got an animation about deer right here. So, for a long time, we've known about the capabilities of virtualization to take big, expensive servers and slice them up into smaller pieces that people can use for use cases that don't need the whole thing. And GPUs have really just exacerbated that and reminded us of how valuable that can be. These GPUs are very expensive. They take sometimes a long time even to get them. So one of these servers with a bunch of GPUs costs an awful lot of money to use, to buy, to use, to operate, to power, to cool. And so we're seeing a lot of need and a lot of motivation to divide up these with VMs or containers, but VMs especially, we'll get a little bit more into that, so that it's just cheaper for everybody. I'm a data scientist. I'm running an inference job that's not all that big and doesn't need all of this, on and on. There's a lot of different kinds of use cases where you don't need the full capacity that you get. And so these techniques of being able to safely and efficiently divide up this capacity have become very important. Now, tenant isolation is where we get into some more interesting topics and more interesting use cases. We're all familiar with Kubernetes and namespaces and the kinds of isolation that we get out of that. But, of course, people still gravitate for a variety of reasons to VMs to add a stronger level of isolation, especially in use cases where the user of whatever's in this VM, be it a Kubernetes cluster where the nodes are virtualized, or be it VMs that have something else inside them. Perhaps it's an AI developer environment or something along those lines. So having a VM isolates tenants from each other, isolates these workloads from each other. So you can even apply these kinds of techniques to then isolate the performance of these pieces of hardware from each other, so you don't have a noisy neighbor problem, and so on. But diving further into tenant isolation, now we get to what's a really fascinating turn of events, I think. This is a huge uprising in demand for new service providers, cloud-type service providers. Small clouds, local clouds, regional clouds. There's a lot of names being thrown around. Neo clouds, sovereign AI clouds, AI factories. I kind of want to, I don't know if you guys have ever had those refrigerator magnets with different words that you can move around in different combinations. I want to get these refrigerator magnets for these words so we can rearrange them and argue about what they all mean in different combinations. But that all being said, here we are, we have this need to have a public service where we are renting out CPU and GPU capacity to users, whether maybe it's in a specific region, like your local region, if you're a sovereign kind of cloud. Often it's very locality based on data gravity. We could have, perhaps there has been a whole other talk about sovereignty and the motivations today behind that. But bottom line here is, what we're seeing is, okay, you want a Virt platform that you can do this kind of thing with, operate a real cloud service on top of. KubeVirt is the obvious choice for a lot of reasons. It enables you, of course, to run containerized and virtualized workloads side by side. It gives you a path to modernization if you'd like to liberate things out of the VM, and on and on. VMs are much faster to provision than bare metal, of course, so that's a huge attractor for these kind of service providers. Even in cases we see where you want to give an entire node, like an entire physical node to somebody at a time, there's still quite a bit of value in virtualizing that node and handing that person a VM with all of that capacity, all of those GPUs in it, just for the characteristics of lifecycle of I can boot it fast, I can provision it fast, and especially having isolation not only between tenants, so two different tenants can't see or interfere with each other, but also this isolation between all of the tenants and the cloud provider themselves. So I don't want to reveal information about the underlying nodes, the performance characteristics, the hardware, the network characteristics that those nodes are attached to. I'm going to abstract all of that into a VM. And this all matches the kind of cloud experience that you've been having with hyperscalers for many years, but now we're seeing this at a much more local level. Maybe as few as just tens of servers can constitute a really valuable local cloud service where a provider can rent out GPU capacity to users in their region. Okay. Now, scaling and lifecycle, this is where it gets more fun. VMs enable, in all of these kinds of use cases, much, much faster boot. So a physical server, especially some of these fancy servers with big fancy GPUs these days, can take half an hour or more just to boot. So when someone comes along and wants to have themselves a VM or a cluster, or they want to expand their cluster, scale out, we don't want to wait half an hour just to boot the thing, and then we write an OS to disk, and then we've got to reboot after that. This is no good. So here's, again, a major point of value for using KubeVirt and using VMs to very quickly be able to stand up, expand, scale in and out, these kinds of things. And another really important lifecycle aspect here is around just the security of the hardware itself. So again, another motivator why we see sometimes even when a provider is renting out entire physical nodes at a time, they virtualize that capacity and hand over the VMs to the end customers. That is to protect the devices and the firmware and prevent that user who now has access and custody of that node, of that compute capacity for some period of time, prevents them from having direct access to a lot of the underlying hardware to be able to influence the firmware and those kinds of things. You can imagine the nightmare that ensues, and it's been done. I see some nods. When you have to clean up an actual bare metal node that's been given over to some other user. Non-Kubernetes nodes, also a huge point of value here. Sometimes it's just very small use cases. I need to stand up an environment to run some job, and then it goes away. But also very large HPC kind of use cases are using this as well. Things like, anybody familiar with Slurm? Slurm users? Okay, yeah. Slurm's been around a long time. People love their Slurm. They're very attached to Slurm. And want to keep using it, and there's a mix of reasons. It's good at what it does, and people are familiar. They've built whole careers on Slurm. So here now we've got an opportunity to either run Slurm in VMs just directly, so you can scale that up and down as you need, or we're seeing even in a big increase in interest in running Slurm in Kubernetes. There's some really interesting projects doing that I would encourage you to go look at if you're a Slurm user. It gives a much more direct then path to say, hey, if you're using Slurm on Kube in these VMs, we can show you how to do the same thing with some other more Kubernetes-native tooling when you're ready. And yeah, so those are the use cases that are really motivating us. I think we've got just a minute or two. Do you want to wrap this up, Ezra?
Yeah, I think I hope that everything was clear enough. The main takeout of this session is that although we're at KubeCon and we are pods, containers, and so on, luckily we have this very nice project of KubeVirt, which is actually a very stable solution. And there are, as Michael mentioned, there are a lot of concrete cases. We get demands from customers. So for example, what Michael said about customers who actually want the whole bare metal, but he's a service provider. He really doesn't want to give that to customers, even if they want the whole GPU. So this is the main takeout. Try to look also on when you have some isolation requirement and so on, keep in mind that you also have the possibility to use VMs on the same platform, together VM as a pod and so on. And also, the nice capabilities of KubeVirt, like injecting XML, playing with everything underneath and so on. And that's basically it.
Yeah, I think, and I would also just emphasize, this is all an ongoing conversation. Much of the reason that we wanted to do this is to raise some flags about, hey, there's work required here to dig in as a community. The landscape has changed even since Ezra and I submitted this talk. It's moving really fast. So if you're interested, stay engaged in this conversation and how DRA is being applied and other techniques here. We need to move this forward for all of our benefit. And I think we are out of time, but we'll hang out for a little bit here, wherever they kick us out in the hall, if y'all have questions. Thank you very much for coming.